Okay, let's dive in. Imagine maybe a futuristic doctor performing surgery, but the tool moves inside the body almost like an octopus arm, super flexible. Or think about a soft prosthetic, something that feels completely natural, operates wirelessly, almost like something Tony Stark would build.
Yeah, that kind of vision.
Yeah.
It's moving faster than you might think from science fiction to actual science fact,
Hmm.
thanks to some really remarkable breakthroughs in soft robotics.
Absolutely. And today we're doing a deep dive into the research making this kind of, well, dynamic, programmable movement possible. And the power source isn't vibranium or anything like that. It's something much more common. It's sound waves acting on these incredibly tiny bubbles.
hmm Our source material today is a really fascinating paper. It was published in Nature. The title is Ultrasound-driven Programmable Artificial Muscles.
Hmm.
This work was led by Zhan Shi and Ziyuan Zhang, with Daniel Ahmed as the corresponding author. And it involves researchers from several institutions, including ETH, Zurich, the University of Minster, and the University of Nebraska-Lincoln.
Right. So our mission for this deep dive is pretty clear. We want to understand this completely new way of thinking about artificial muscles. How exactly did they get such complex, fast, and scalable movement using ultrasound on microbubbles? And maybe more importantly, what does this actually mean for fields like medicine and robotics?
Yeah, and to really get why this is such a big deal, I think we first need to talk about why making artificial muscles is so hard in the first place. I mean, muscles in nature, they're the inspiration, right? They allow animals to move with such grace and complexity. But our current artificial muscles, things like pneumatic systems or ones based on tendons, they tend to be, well, clunky.
Yeah, clunky is a good word. You see these factory robots, very rigid. And when you try to mimic something soft and complex, like, say, a human hand or even a tongue, the current artificial muscles, they need this incredibly complicated setup, tubes, wires, tethers. It gets messy fast.
Exactly. The more complex the movement you want, the more complex the control system needs to be. It's a scaling problem. And when researchers try to cut the cord, go fully wireless to solve that tethering issue,
They hit a whole new set of problems, right?
right, they run into some pretty fundamental limits.
Okay, let's walk through those limits. Because the current wireless methods, they sound good on paper, but
Well, take chemical actuation. It sounds convenient, maybe, but the chemicals can be toxic. Plus, they need a constant fuel supply, not ideal for inside the body.
okay, so chemicals are tricky. What about light or heat?
Light and temperature-based systems, they have trouble penetrating deep into tissue without losing a lot of energy, and there's a real risk of thermal damage. You really don't want to accidentally cook the surrounding tissues when you're trying to, say, help a heart muscle.
Definitely not. Okay, what about magnetic systems? We see those in movies all the time, particles moving around like magic. Surely that's the answer.
Magnets are powerful, no doubt, but they usually need really bulky, high-power external hardware to generate those strong magnetic fields. Think big MRI-like machines. And maybe worse, they can cause something called joule heating. That's unwanted heat generated by electrical resistance. Especially if the device is working continuously. It just requires too much equipment, too much heat management. It's not practical for tiny, soft robots working deep inside you.
Right, so that brings us back to sound. Why did ultrasound, acoustic energy, turn out to be the kind of breakthrough solution here?
Ultrasound really hits the sweet spot for soft robotics, especially for medical uses. For one, it doesn't really care what material it's going through. It penetrates tissue deeply. It allows for wireless control naturally. It's totally biocompatible. We use it for imaging all the time.
Hmm.
Plus, it's fast. We're talking millisecond scale responsiveness. And maybe the most practical point, it works with the standard clinical ultrasound machines that are already in hospitals worldwide.
So it's accessible, non-invasive, fast, ticks all the boxes.
Exactly. It's a ready-to-go energy source, in a sense.
Okay, this is where my mind starts to bend a little. How do you take a sound wave, which is invisible, silent, and turn it into a physical force? Enough force to make a muscle contract and do it in a way that you can program.
Right. That's the core genius of the work by Zhan Shi and the team. So the artificial muscle itself is built on this thin, flexible membrane. Usually it's polydimethylsiloxane, or PDMS.
PDMS, isn't that just a fancy term for a type of silicone, like the flexible stuff?
Pretty much, yeah. And that material choice is actually crucial.
Why? What's so special about silicone here?
It's because PDMS gives you that perfect blend of flexibility and compliance. You need that for soft robotics. If the muscle material were stiff, the tiny little forces from the bubbles wouldn't be enough to make it bend or change shape in complex ways.
Well,
PDMS lets the whole structure respond dynamically, even to really small localized forces.
Okay, so the flexible silicone shell is important. What's inside?
Inside the shell, they embed, get this, over 10,000 microbubbles in a single sample. The density is incredible, about 3,000 microbubbles packed into every square millimeter.
3,000 bubbles per square millimeter. That's dense. That density must be how they get such fine control, the programmability.
That's exactly it. And the key to making it programmable is a physics principle,
Mm.
resonance frequency. Think of it less like a simple on-off switch and maybe more like tuning an old-school radio.
Okay, I like that analogy. Tuning a radio.
Yeah. Each one of those thousands of microbubbles is deliberately made with very precise but slightly different dimensions, different sizes. And these different sizes mean they each have their own distinct natural frequency they like to vibrate at.
Ah, okay. So if the researchers send in an ultrasound wave at, let's say, 100 kilohertz.
Then only the bubbles that are tuned to resonate near 100 kilohertz will start oscillating really strongly. All the other bubbles, the ones at different sizes and frequencies, they basically stay quiet.
They're tuning the system, selectively activating specific bubbles.
Precisely. And they use what's called a sweeping frequency ultrasound excitation. You can kind of picture it like quickly running your finger across a set of very precise radio channels. As the frequency sweeps, different sets of microbubbles along the muscle get activated, one after the other, sequentially.
And when a bubble oscillates, it pushes the fluid around it, right? Creating a tiny jet of force. The paper calls them distributed point thrusts.
That's right, tiny, localized jets of force.
So sweeping the frequency isn't just turning the muscle on or off. It's telling specific parts of the muscle to flex and when to flex, dynamically.
That is the really revolutionary part. By orchestrating this selective sequential firing of bubble arrays, the muscle can achieve these incredibly complex, dynamic, multi-mode shapes. You're not just limited to simple bending anymore. You can create movements that really mimic nature, like an undulating wave, or the way a stingray's fins move.
That is amazing control just by changing the sound's frequency. Okay, let's talk numbers. Performance, because the speed and the force here sound impressive.
Yeah, for how small and light they are, these acoustic muscles pack a punch. They measured a force intensity of about 7.6 micronewtons per square millimeter, which is quite significant at that scale. And they are incredibly lightweight, only 0.047 milligrams per square millimeter, almost nothing.
Okay, the force is decent, but I think you mentioned speed earlier. The sources highlighted something like sub-100 millisecond response times for gripping. That sounds like the real game changer, especially for biology, faster than blinking.
That speed, that millisecond response, is absolutely vital. It allows for precision, but it also helps prevent damage. If you're trying to interact with something really delicate, like living cells or tissues, being able to move quickly, precisely, and programmably opens up possibilities that slower, clunkier robots just couldn't handle.
Okay, let's jump right into those applications they demonstrated, because this is where it gets real, starting with the soft gripper.
Right. They built this prototype gripper made of multiple soft muscle petals, and its job was to handle a live zebrafish larva. Zebrafish larvae are notoriously fragile, so it's a great test for delicate manipulation.
And how did it do?
It was pretty stunning. The gripper closed and grasped the larva in under that 100 millisecond window, fast enough to catch it. But here's the critical part. When they turned the ultrasound off, the larva just swam away, completely unharmed, which really confirms the biocompatibility, the precision, and how gentle this ultrasound-driven force can be.
Wow, no damage. That's huge for handling biological samples. Okay, what else? They mentioned a robotic skin.
Yes, this is another really cool concept. The artificial muscle material can be used as a flexible, conformable skin. You can basically stick this skin onto an object, and the skin itself imparts motion to that object, wirelessly.
So you're essentially giving static objects their own little engine, a silent wireless propulsion system you just slap on.
Kind of, yeah. They showed it working by attaching the skin to, of all things, an almond, an arbitrarily shaped almond. And they made the almond rotate just using the ultrasound on the skin. They also stuck it onto a blade of grass and made the grass bend on command. Shows it can self-adhere and create very localized movement.
Okay, an almond and grass leading up to the main event. The bio-inspired robots. We have to talk about the Stingray bot.
Ah, yes, the Stingray bot. This was a biomimetic robot designed to swim like a real stingray. It had two artificial muscles acting as its side fins, like pectoral fins. And the key was that they embedded microbubbles of varying sizes along these fins, bigger near the body, smaller towards the tips.
Ah, variable sizes again, so when they did the frequency sweep.
Exactly. The sweeping frequency caused the fins to move with that beautiful, fluid, undulating motion, that wave-like ripple you see in real stingrays.
Just like the real thing swimming. And did it actually move?
It did. That undulating motion was surprisingly effective for propulsion. The stingray bot swam forward at an initial speed of about 0.8 body lengths per second. That's pretty respectable and shows real mobility potential in water or potentially bodily fluids.
Which brings us squarely to medicine. The fact that this is all powered by biocompatible ultrasound, the medical potential seems enormous.
Huge. And they push this boundary by testing it ex vivo, using pig organs, which are good models for human tissues. First, they took that robotic skin and attached it to the outside surface of a pig heart, the epicardium, and it stayed stuck and functional under continuous ultrasound activation for over 60 minutes.
60 minutes on a heart. That suggests maybe a future cardiac patch,
Yeah.
delivered wirelessly, held in place by sound, maybe helping the heart beat without needing stitches. That's kind of mind-blowing.
It really opens up possibilities like that, yes. Then they took it a step further. They put the artificial muscle inside a tiny biodegradable capsule. They released this capsule inside an excised pig bladder and then used the ultrasound to make the muscle attach itself to the inner wall of the bladder, showing remote deployment and anchoring inside an organ.
Wow. And the final piece was navigation, right? Inside the body.
Yes, they took the stingray bot itself and successfully navigated it through complex ex vivo pig gastrointestinal tissues, the stomach, the intestine. The movement was entirely controlled remotely using ultrasound, and the robot itself is soft, remember.
Like a tiny, soft submarine exploring a complex cave system, but it's inside the GI tract. This has got to have massive implications for things like targeted drug delivery, right? Or minimally invasive procedures, getting tools into places where rigid wired scopes can't easily go or might cause damage.
Absolutely. Navigating these complex, folding biological environments so gently. It really paves the way for, say, delivering gene therapy to a very specific spot or releasing drugs exactly where they're needed in the gut. It's moving towards that promise of truly personalized, non-invasive treatments.
Okay, this sounds almost too good to be true. No technology is perfect right out of the gate. What were the limitations the researchers themselves pointed out, Zhanxi and the team?
They were upfront about a couple of key areas needing more work. First, the microbubbles inside the cavities tend to grow slightly during prolonged operation. This makes the actuation unstable after about 30 minutes of continuous use.
Ah, okay, so right now it's more of a sprinter than a marathon runner.
Pretty much. Though they did note that just resubmerging the device in water seemed to reset it. And they suggested that sealing the bubble cavities better in future designs could probably solve the stability issue for longer operation.
Okay, makes sense. What was the second limitation? Something about distance.
Yeah, power transmission. The actuation force depends on how far the muscle is from the ultrasound transducer, the sound source. They found the deformation, the amount it bent, dropped by about half, 50%, when the distance increased from 1 centimeter to 5 centimeters.
A 50% drop at 5 centimeters. But that sounds significant. Does that limit it to things near the surface, or is 5 centimeters actually workable for internal stuff?
Well, for many internal procedures, 5 centimeters is actually a reasonable working distance. But for true deep body, untethered operation, they definitely need to optimize the power delivery. The authors mentioned solutions, though, things like using high-intensity focused ultrasound, or HIFU, and also playing with the geometry of the bubble cavities themselves. They found certain shapes, like converging trapezoids, actually generated much stronger forces. So there are engineering paths forward.
Okay, so the next steps sound like boosting the power and endurance, maybe refining the designs. What's the big vision, according to the authors like Daniel Ahmed?
They're really pushing towards making these devices out of fully biodegradable materials, like hydrogels. Imagine a temporary medical device that does its job and then just safely dissolves away. And by boosting performance with things like HIFU and optimized geometry, they aim to get really fine millimeter-scale local control, which, as you said, is exactly what you need for super-targeted drug delivery or maybe even localized gene therapy, all done silently and wirelessly.
That level of customization, the scalability with these bubble arrays, It really does feel like these acoustic artificial muscles could be a cornerstone for future synthetic systems.
It definitely shifts the paradigm for how we think about movement, control, and especially non-invasive access within the body.
Okay, so let's wrap this up. Let's crystallize the three big takeaways for you, our listener, from this deep dive into the Nature paper by Zhan Shi, Daniel Ahmed, and their colleagues.
Okay, takeaway number one. The wireless revolution is here for artificial muscles. We now have a practical, highly programmable wireless control system using common ultrasound. It gets around the old problems: bulky hardware, toxic chemicals, poor tissue penetration.
Takeaway number two, frequency is force. This is the core magic. By engineering these tiny microbubbles to respond to specific sound frequencies, they can create customized, localized forces. This unlocks true programmability, enabling complex, dynamic movements from gentle gripping to swimming like a fish.
And takeaway number three, a soft biomedical future. Those prototypes, the gripper gently holding the zebrafish, the stingray navigating pig intestines, they show massive, immediate promise. This tech gives us tools that can navigate tricky biological spaces and interact safely with soft organs, opening doors for non-invasive therapies and diagnostics.
Yeah, this research really shows that the future of robotics, especially in medicine, looks soft, tiny, and remarkably powered by sound. It's a huge leap towards medical tech that's more personalized, conformal, and less invasive.
It really demonstrates how sometimes the simplest physical principles, like resonance, can lead to incredibly sophisticated technology.
So here's a final thought to leave you with. If just by tuning sound waves, we can give life and precise movement to a tiny robot inside the body using these silent microbubbles, what other complex biological systems could we potentially influence or even heal just by figuring out the right way to tune the sound? Maybe something to ponder the next time you hear a low hum from an everyday device.